All right, 7.4, there is an actual postulate for similar triangles. Just triangles, but it is a postulate, therefore it is true. We're going to use the angle-angle similarity postulate to prove triangles are similar and then prove other things. That's right, so we're getting a little bit back into proofs today. And so the angle-angle similarity postulate just simply says if two angles of one triangle are congruent to two angles of another triangle, then the triangles are similar. And basically we know from the corollary that states that if two angles of a triangle are congruent, so are the third. And when we also talked about two angles of the triangles being congruent, the fact that we know that the angles are congruent also tells us that the sides have some sort of proportion with one another, or they wouldn't be able to create those angles. So even though we define a similar figure as a figure that has corresponding sides in proportion, when you're talking about triangles, it's impossible to create those angles without having the relationship of their three sides to be in the same proportion. So whether it's 70 and 70 and 40, or whether it's another measurement of 30, 75, and 75, we're always going to have that ability to do that. Now, they don't necessarily have to be the same thing as an isosceles triangle. However, we can then prove if it is an isosceles triangle, then and the angles are congruent, they are also similar. These measurements can be anything. They don't have to be an isosceles triangle for this to happen. Take a second now, look at questions 1 through 6 and see if you can determine based on that postulate whether or not you have a pair of similar triangles. Our next example is example 1 on your worksheet, so if you don't want to cheat, don't look at it. But we're going to try to find x and y, and the given information is that we know that these two lines are parallel. We don't know, obviously, that these two lines, these two segments are congruent. However, we could create a proportion, and here's the hint that I'm going to give you. We can actually break up this triangle into two pieces, the small triangle and the large triangle. Given that information, we could then form a proportion to solve for x and y. You should find that with that, x equals 10 and y equals 5. You could also look at this and see that 8 to 4 in terms of the two triangles would then form a proportion where this segment here is double the bottom segment, creating half of 10 to be y equals 5. The proportion here, though, for x and 15, don't forget, it's the small triangle with 8 and the large triangle with 12. Many people who make this mistake say that it's 8 over 4 equals x over 15 because 15 is on the bottom. Keep in mind that the 15 represents the side of the large triangle, and so does 12. So your proportion would be 8 over 12 equals x over 15 to get x to equal 10. Hit pause right now and answer questions 7 through 12, trying to find the values of x and y based on the example we just did. So in the next example, we do get back into proofs because we do obviously have a postulate to use. And so we have the given statement that AC is parallel to BD, and we're supposed to prove that triangle AOC is similar to triangle BOD. Now to do that, we need to do a couple of things. We either need to prove angle-angle, or we need to prove that all sides of the triangles are proportional. In this case, we have some given information that may help us in doing that. And so we use the given to then prove that angles A and B are congruent and angles C and D are congruent. And because the parallel lines exist, we have alternate interior angles. We could then prove that AOC and BOD are similar because of the angle-angle postulate. Now you could go back and also include that angles AOC and angles DOB form vertical angles, but then keep in mind if you were trying to do the least amount of steps, you would also have to include alternate interior angles as one of the steps, and then you would therefore have 4 steps. It's not wrong, there's nothing wrong with it, it's just, you would have an extra step there. Another example here, we have two triangles. We know that AB is parallel to BF, RH is perpendicular, and RH is perpendicular to AF, and we also know that 1 and 2 are congruent. Except take a look at the proof statement. HR times BF equals BA times HA. What do you think we were trying to do there in order to determine the products of those two segments to be congruent to the products of the other two segments? Hopefully you said that the similar figures would form a proportion, and that the proof statement is simply an extension of the means extremes property. Therefore, the product of H and R could be the means, HR and BF could be the means, and BA and HA could be the extremes, creating the proportion and just going one step further. Take a second and see if you can get to that point where the product of HR and BF equals the product of BA and HA. So let's see what we came up with here. We have the given information all at once. We don't have to use it all at once, but again, it could help. Once we know that they're perpendicular and the lines and the angles are congruent, we can go right into the fact that their definition of perpendicular lines, and then therefore they are congruent. Any way you wanted to say this is fine. If you want to say they're 90-degree angles, you want to say that they're congruent, we can say that. But obviously we have to state something about the angles being congruent. Therefore we know we could then use the next statement that the two triangles are similar. Once we know the two triangles are similar, we can then make the statement that the proportion of HA to BF is proportionate to the sides of HR to BA as they are corresponding. And so the reason is corresponding sides of similar triangles are proportional. It's not CPOSTP, but you could probably imagine that you could come up with some sort of abbreviation for it. After that, again, we could use the means extremes property, cross product, properties of a proportion, any one of those reasons to then prove that the product of HA to BA, again, cross multiplying, equals the product of HR to BF. And again, it's just taking it one step further onto the proof. Take a second now, enter the rest of proof number 13, which includes the example in the given information on the back of your worksheet. The last example is actually number 14 on your worksheet. The given information is that AB and CD intersect at P, and that angle DAB and DCB are congruent. Your job is to prove that the product of AP and PB is equal to the product of CP and PD. Hit pause and try to answer that proof now. You're going to have to answer this one and then bring it in tomorrow for the final proof results.